So let's begin with another kind of problem-solving situation which involves molar heat. Now remember, molar heat is working with situations where the object is undergoing a change in state. When there's a change in state going on, also called a phase change, the temperature doesn't change because the heat entering the system is not increasing the vibration. Instead, you have an increase in the spacing that's going on. So here's our first problem. We say that how many kilojoules of energy are required to vaporize 135 grams of benzene, C6H6. The heat of vaporization for the benzene is 30.8 kilojoules. Now, where do we get this value? And the answer is it comes from a table. And what you can see is the table lists values of molar heat for different substances. It lists its value for specific heat values when temperature is changing. And this last one is one we have not talked about yet, which is this is the heat of formation, which is part of the heat of reaction calculation. We'll look at those later. So it says that we're looking for the heat of fusion for benzene, and therefore we're going to have to take a look at this table here, which is molar heat. Now what we're going to notice is that the molar heat for benzene, when we're vaporizing it or turning it into a gas, is 30.8. And so that is where we get the value that we're going to work with. So let's draw a picture of what's happening. We have in here a container, and that container contains liquid benzene. And what we're going to do is take that liquid benzene and we're going to turn it into a gas. And the reason we know it's going to turn into a gas is it says we're going to vaporize it. Now during this change there is no temperature change. It is simply going to be turning it into a set of gases arrangement here. So this is going to be a vaporization process. Now vaporization requires, I can't write very well at all, my apologies, but vaporization is going to require an input of the heat. And so let's label this as heat. And so heat is going to be entering the system to cause the vaporization of benzene here to go to a gaseous state here. Now we symbolize heat with the letter Q. And again, a critical piece is we're inputting heat because it requires the heat energy to create the separation. Now molar heat, the equation says that Q is equal to the delta H times moles, which is the amount of material. Now, because what we're doing is vaporization, the delta H value is the delta H of vaporization. And that was the value that we had looked up on the chart. So what we're missing is this right here. And now we simply punch the values in. But notice, we have 135 grams of benzene, but I don't want it to be in grams. I need the amount to be in moles. So what we're going to have to do is convert the weight in grams into moles. So what we're going to do is, we've done this many times before. We have benzene. which is C6H6. So what we're going to do is figure out the molar mass. Carbon, rounding it off, weighs 12. I have 6 of them. Hydrogen weighs 1. I have 6 of them. So this is going to be 72. This is going to be 6. And so the weight of 1 mole of benzene is going to be 78 grams per mole. But I don't have 78 grams of it. I have 135, and therefore we take 135 over 1. We take 78 grams is 1 mole. We do our calculations, and you have 1.73 moles. So that's how many moles of benzene we're going to be vaporizing. So now what we do is we have a chance to now plug our values in. So Q is going to be equal to the delta H of vaporization. That's a standard value, and that's going to be 30.8 kilojoules per mole. How much benzene are we working with here? We're working with 1.73 moles. My writing continues to be very poor. I'm sorry. Our moles cancel out. And so, the amount of heat that has to flow in to cause the liquid benzene to turn to a gas is equal to 53.3 kilojoules. Now there's one last idea that you must keep straight, which is this heat is flowing in. So the system, which is liquid benzene, the system is gaining the heat in this process. Therefore, Q is a positive value because the heat is being gained. Therefore, we call it an endothermic reaction. Now let's take on another problem. It's going to be still a molar heat problem. However, we're going to work with a different substance. In this case, the substance is going to be methanol. Now, once again, because it's molar heat, we're not going to change temperature when we add or subtract the heat. We're going to change the state or the phase. Now, in this case, what it says is, what is the mass of a sample of methanol that releases 5 kilojoules of energy as it solidifies? So when you see the word solidifies, we're changing it from a liquid state to a solid state. And it tells us the basic value, which is the heat of fusion for methanol, is 3.16. So what we're going to be doing is we're going to be taking a container of methanol. It's a liquid. What we're going to do is we're going to turn it into a solid. Wow, not well drawn. Bear with me. So, when we carry out a solidification, when we change it from a liquid to a solid, what you have to do is you have to draw heat out. by drawing the heat out, we can make the spacing get closer. Now, because the system, the liquid methanol, is releasing this heat, we call the reaction exothermic, because there's a release or loss of heat from the system as it turns to a solid. So what's interesting about this problem is it tells us how much heat got released. So the amount of heat that was released is going to be 5 kilojoules of heat. So whenever the change of state, whenever it's molar heat, our equation is going to read Q is equal to the delta H times moles. Moles tells us how much material we are freezing in this case. Now, changing from a liquid to a solid is referred to as a fusion. So what we do is we look up on the chart. It's a molar heat problem. We're working with methanol. What are you doing with methanol? We're solidifying it. Because it's freezing, it belongs in the category of a delta H of fusion. If, with this methanol, if we were vaporizing it, then the delta H of vaporization would be used, which would be here. But since we're turning it to a solid, we're going to use the heat of fusion value, which is 3.16. So we're going to use the delta H of fusion. Okay. Now, we know what the Q value is. The Q value is 5.0 kilojoules. We know what the delta H of fusion is because we looked up on the chart. It's also listed right here. So it's 3.16 kilojoules per mole. The question is, so how many moles is that? Well, that's what we're trying to find. Now, yes, I'm aware that it actually isn't asking for moles. It actually is asking for the mass of the sample. Now, this equation only gives us the number of moles. So as you might suspect, once we know the moles, we will have to further make a change. Now, there is one last item we need to account for here. The item is that this process is losing heat from the system. We have to indicate that the heat law is being lost in this process. So we're going to use Q negative because the loss is what is taking place. So when we add the numbers into our equation, minus 5.0 kilojoules is equal to 3.16 kilojoules per mole. this is going to be X moles. So what happens is we cancel out the moles, we multiply through, and we have negative 1.58 is equal to X, which is the mole count. Now what we have to do is say if I've got 1.58 moles of methanol, how many grams is that? Well, CH3OH, its molar mass, or moles, grams per mole, is going to be 32 grams per mole. So let's convert this now. I have negative 1.58 moles over 1 times 1 mole, 32 grams, and therefore my molar mass is going to be 50.56 grams. Now again, the negative is there because it's telling me that the direction that the heat is moving is out of the system. So this is the amount of grams, which I cannot have a negative weight, but this is the amount of grams of methanol that underwent the solidification because 5 kilojoules of energy was released.